Hello everyone. Today we are going to continue with our Unit 4, Chemical Equilibrium. Today we are going to do a little calculation, which is a very simple calculations. Of course, the last lesson we did, Le Chalais principle, we discovered the way system adjusts itself to remove the stress, like addition or subtraction of a reactant or product, so that equilibrium can be maintained. All right, chemical equilibrium was discovered by two gentlemen, Cato Maximilian Goldberg and his brother-in-law Peter Wage. They both developed what we call the mass action, which is going to be basis for today's lesson. But before we move on, let's check out some of the facts we need to know about that. This is a recap of what we did in the Chalais principle. Under chemical equilibrium, we discussed that reversible reactions are reactions that products can react to reform the reactants. You're familiar with that? And chemical equilibrium, when the rate of forward reaction equals the rate of the reverse reaction, and the concentration of products and reactants remains unchanged. That means when your forward and backward reaction are the same, the form and reform at the same rate. That is when chemical equilibrium is attained. And on that note, we use this equation as example. We have mercury oxide solid decomposed to mercury liquid plus oxygen gas, and then mercury liquid plus oxygen gas recombine again to form your mercury oxide. So this is your equilibrium sign. The arrow forward and backward indicates equilibrium in action. Right, this is another example we used during the Le Chalais principle. Now these are two, this is a reactant, breaks down to give you two products. The reactant here is 2NO2, which is at the top. The concentration is very high at the beginning of the reaction. But for NO and O2, the concentrations is 0 before you start the reaction. Now, the moment you start this reaction, the concentration of this, of course, reduces. As you break this down and you're forming this, it reduces the reactant but increases the product. So let's look at it this way. When this breaks down, the reaction goes on and the amount of NO2 decreases because it's forming NO and O2. NO and O2 are increasing while NO2 is decreasing. It will get to a point when the amount of NO2 or the rate of decomposition of NO2 and the rate of formation of NO are equal. This is the point. That's when equilibrium is achieved. And then here the equilibrium continues, or the decomposition continues until the equilibrium for oxygen is attained. So this point is the point at which the rate of formation of oxygen is equal to the rate of decomposition of NO2. So these are the two equilibrium points for this reaction. Exo and endothermic reactions. What is exo and endo? Exothermic reaction gives out heat as part of the product. That means the heat sign is going to be on the product side. Temperature increases after the reaction. That means the container becomes cold, becomes hot. The surroundings becomes very warm because energy is dissipated to the surroundings. So energy is given out. That is why the heat sign is on the product side. And of course, it also means the heat, change of heat is negative. It's negative. I'll just give an example here as negative 848 kilojoules. Then, on the other hand, On the other hand, the exothermic reaction absorbs heat from the surrounding. So the container becomes colder than how it started. In this case, the reaction, the heat has the reaction has the rates, the heat on the reactant side, unlike the exothermic when the heat is on the product side. Here, the heat sign is on the reactant side because heat is absorbed into the system. So the temperature of that container drops down, becomes colder. All right? And this change of heat will be positive. It will go to a positive sign. Now the law of mass action. For the reaction Ja plus Kb in equilibrium with Lc plus Md, where J, K, L, and M are coefficients of a balanced equation. So it is worthy to note that if you are given an equation, the first thing you need to look at is if the reaction is balanced. The reaction is balanced, then you can move on. If it's not balanced, the first assignment is to balance the reaction. Alright, so we have covered a lot about the balancing equation. If you're still confused on that, you'll go back and watch the video. Alright, so your J and K are your coefficients, your L and M are the products coefficient. So in this case, for the mass action is going to be products over reactant. Whatever you produce over whatever you started with. So your C and D are your reactant, are your products. L and M will be your coefficient. So your coefficient becomes the exponent. Let me use the sums. Your coefficient becomes the exponent. The coefficient here becomes the exponent. And then over the reactant, which is concentration of A times concentration of B. Now it's worthy to note that this is the sign we use for concentration. We don't use parentheses. We use brackets to represent concentration. So if you draw this in chemistry without even writing anything there, we know it stands for concentration. So just in case, remember that this stands for concentration. All right? So the law of mass actions is that products over reactants, and your coefficient becomes your exponents. Just like that. As simple as that. So where K, this K is called your equilibrium constant. Your K is your equilibrium constant. But let's define the values of K. When your K is large, this shows that the product is favored, meaning that your reactants moves to your, the equilibrium moves to your right, because that is where your product is. So in this case, more products are produced. So more of reactants combine to give you the product when equilibrium is achieved. When you have a small K, that is when your answer is K, or the answer of K is very small. In that case, more reactants are produced. That means your product breaks down much more than the reactants are being combined. So that means you have more reactants being formed. This is just like when your equilibrium shifts to your left. It's the same thing. We're just using a different language because we are now looking at the value of K. Alright, that means when equilibrium is achieved, very little reactant has been converted to a product. So that means very little of this is converted, so more reactants are formed. So reactants are favored. So your equilibrium shift to your left. So let's see how do we write this mass action. Write the expression for the reaction 2NO2 to give you 2NO plus O2. Remember, it is product over reactant, and your coefficient becomes your exponent. So what we're going to do is, this is your coefficient, this is going to be your exponent, so it's going to be this way, NO squared O2 1, because this is coefficient is 1, so there's nothing here. Remember, it is product, this is your product over reactant. So reactant is NO2. Remember, the coefficient here is 2, so we're going to have a square here. All right. So the coefficient becomes the exponent, so that is what you have. You have NO to give you this. This is your coefficient, becomes your exponent. Your O2 goes down here. There is no coefficient, or let's say just 1. Then your reactant will be NO2. The coefficient here is 2, so that 2 goes down there. Any question? Just let me know. Now, this is just the same thing as we just explained. When the balance equation for a reaction is multiplied by a factor of n, the equilibrium expression for the new reaction is the original expression raised to the nth power. Nth power is the coefficient that you have, which is this, nth power coefficient, 2, 2 to 1. Remember, we did the mole ratio. The ratio of this is 2 to 2 to 1. So this NO, the coefficient here is 2, so it becomes the exponent. NO2, the coefficient here is 1, so of course you don't need to write 1, it doesn't change anything. And then over reactant, which is NO2, the coefficient here is this 2. Is right, these 2 right here. So let's see, how do you write this? This is challenge 1 for you. Get a pencil or paper and do this for 10 seconds. Alright, if you get something like this, that's absolutely correct. NO, products, concentration times O2, then the coefficient here is half. So this half becomes the exponent here, right here. And NO, the coefficient here is 1, so doesn't have any exponent. So let's look at equilibrium expression for solid and liquid. Now, write the equilibrium expression for H2O solid plus heat to give you H2O gas. Now, I'm giving you instruction here that any equilibrium expression for liquid and solid is always 1. There is no equilibrium expression for them. It's always 1. But you still have to write it there, because sometimes that 1 can be at the top, which is going to be a fraction. So don't just straight away. It is very important for you to write the expression for that. But just put 1 in there. So in this case, the equilibrium expression, K expression, for this one is going to be H2O gas over 1. Because this is what? This is solid. So it's going to be H2O over 1. Because the expression for this is going to be 1. So that means the answer is going to be just H2O. H2O over 1 is going to be H2O. The position of heterogeneous equilibrium does not depend on the amounts of pure solid or liquids. Meaning that if you have heterogeneous expression, What is heterogeneous? Hetero means many or different. In this case, we have solid, liquid, gas. That means it's very important for you to check the state of that compound or the element you are given. Make sure it is not solid, it is not liquid. If it is either of them, then the expression is going to be 1. So for instance, in this case, the equilibrium expression for this is going to be going to be, remember this is solid and this is liquid. So this and this is going to be 1. And this is going to be the only expression that you have. So it's going to be Cl2 over, Cl2 times PCl3, which is 1. So it's going to be Cl2 times 1 over 1. So it's going to be something like this, 1, because this is liquid, over 1, which is solid. So solid and liquid will be 1, each one. So that will be your final answer. So therefore, the K of P is going to be PCl2. That is the equilibrium expression for chlorine. So let's do some calculation now. Get your calculator, your pencil, or your paper. Write the expression for the following and calculate the KEQ. At the equilibrium point in the decomposition of phosphorus pentachloride to chlorine and phosphorus trichloride, the following concentrations are obtained. The first thing is to write the expression. This is homogeneous equilibrium, so everything counts. Write the expression is PCl3 times Cl2 over PCl5. And you are given the values of PCl5 0.01, PCl3 0.15, Cl2 0.37. So just plug in the values into them. PCl3 is 0.15, Cl2 is 0.37, and PCl5 is 0.10. So when you multiply 0.15 times 0.37 divided by 0.101, you will get 5.55. All right? All right, got it? Practice 2. This is a tricky one. In this case, we have 2 SO2 plus O2 to give you 2 SO3. The value of SO2 is 0.225. Oxygen is 0.15. And this is present in 4 liters flask of at equilibrium at 100 degrees. These are just the conditions. You don't have to bother yourself with these two numbers. But the KEQ is given. So you're looking for SO3. So remember, the first to do is to write the expression. KEQ is the product of our reactants, which is SO3 squared, because this 2 is the coefficient, so it becomes the exponent. Divide by SO2, 2 is the coefficient, becomes the S2 becomes the exponent. And oxygen is just 1. So plug in the values. When you plug in the value, 60 is your KEQ, equals to SO3 squared. Remember, this is SO3 squared from here. All right, SO2 is 0.225, also squared from this expression, and O2 is 0.15. So what to do is to multiply them out. 0.225 squared times 0.15 will give you 0.00759375. The next thing is to cross multiply. Multiply 60 by this SO3 by itself, by 1 rather, because this is over 1. So this is going to be, this is more or less like, this is over 1. So that you multiply this, cross multiply this by that by that, you will get this expression. All right, so how do you find your SO3 now? Find the square root of both sides. Of course, when you multiply this out, 60 times 0. All this number will give you 0.45565 equals to SO3 squared. So find the square root of both sides. The square root of a number, the square root of a square of a number is this number. So what I'm saying is, those of you are still back, or probably you're forgetting your mathematics. What I'm saying is, if I have 4 squared, square root of 4 squared is 4. Oops. Find the square root of 4 squared is 4. Why is it that? Let's open it up. What is 4 times 4? 16. Right? We just will square the choose first, the 4 square. 4 times 4 is 16. Now, you now find the square root of 16 going to be 4. So the square root of a square is just the number. So the square root of SO3 square is the same thing as SO3. SO3. So the square root of 0.455625 would be 0.68. All right, any question, let me know, send me email, so you can take your time, go over this one by one before you take the ticket at the door. All right, so this is what you're going to do for me. You're going to solve this assignment, 7 questions. Question 1 to 5, you write only the expression, the equilibrium expression. And then remember, look at the state of the matters. Look at the solid, liquid, and gas. If it is solid and liquid, it's going to be 1. Maybe they are gases, then you have to look at the expression and check if they are all balanced. I think they are all balanced, so you don't have to, but still try to check. Anytime you have a question like that, try to check the equation, make sure they are balanced. So question 1 to 5, you solve, you write the expression. Question 6 and 7, you have to do some calculations, some tricks. So you have 7 questions, and I want them sent to my email. Share them with me in your Google Classroom. If there's any question, send me email, then we can talk about that. Thank you. That's the end of this lesson for today. See you another time for the continuation of the topic. Thank you. This is Mr. A signing off.